Engine installation is a critical phase in automotive, motorcycle, and machinery assembly, involving precise alignment, secure mounting, and proper connections to ensure optimal performance. The process varies based on engine type: internal combustion, electric, hybrid, and the intended vehicle or machine. Key steps in engine installation. 1. Preparation. Ensure all components, such as the engine, transmission, and mounts, are ready. Verify compatibility between the engine and chassis. Gather necessary tools like an engine hoist, torque wrenches, and alignment gauges. 2. Positioning the engine. Use an engine hoist or crane to carefully lift and position the engine in the engine bay. Align the engine with the mounting points on the chassis or subframe. Check clearances to avoid interference with other components. 3. Mounting the engine. Secure the engine using engine mounts, rubber, hydraulic, or solid mounts, depending on application. Tighten mounting bolts to manufacturer specified torque values to prevent vibrations and misalignment. Ensure proper weight distribution to maintain vehicle balance. For connecting systems, transmission. Attach the transmission to the engine and ensure proper engagement of the flywheel or cooling system. Connect radiator hoses, coolant lines, and the water pump. Fuel system. Install fuel injectors, fuel lines, and ensure proper pressure regulation. Electrical system. Connect the battery, ignition system, sensors, and control units. Exhaust system. Attach exhaust manifolds, catalytic converters, and mufflers. 5. Final checks and testing. Fill fluids, oil, coolant, transmission fluid, etc. Perform a preliminary engine start to check for leaks, abnormal noises, or warning lights. Run diagnostic tests to verify engine sensors, fuel delivery, and ignition timing. Conduct a road test for vehicles, or operational test for machinery, to assess performance under load. Challenges in engine installation. Misalignment can cause vibrations, excessive wear, or drivetrain issues. Electrical faults. Incorrect wiring may lead to ECU errors or failure to start. Fluid leaks, loose connections in coolant, oil, or fuel lines can cause serious damage. Engine installation. A deep dive. Engine installation is a precise and complex process requiring careful planning, proper tools, and a deep understanding of the vehicle or machine. Whether it's a car, motorcycle, truck, or industrial machinery, engine installation must ensure reliability, performance, and safety. Below is a comprehensive guide to engine installation, covering different scenarios and challenges. 1. Preparation for engine installation. Before installing an engine, thorough preparation is essential to avoid delays, misalignment, or damage to components. Tools and equipment required. Engine hoist, crane, for lifting and positioning the engine. Torque wrench, for precise tightening of bolts. Engine stand, for pre-installation assembly. Jack stands, lift, to raise and secure the vehicle. Alignment tools to position the engine accurately. Gasket sealants and thread lockers. For leak-proof sealing. Pre-installation checks. Inspect the engine for damage, cracks, leaks, loose components. Check engine mounts for wear or damage. Replace if necessary. Ensure all necessary components are ready, including sensors, wiring harnesses, and fluid lines. Verify engine compatibility with the vehicle's frame, transmission, and electronic systems. 2. Engine installation process. The installation process varies depending on whether the engine is new, rebuilt, or a swap. However, the core steps remain similar. Step 1. Positioning the engine. Use an engine hoist or crane to carefully lower the engine into the engine bay or chassis. Align engine mounts with the designated mounting points. Make sure there is proper clearance between the engine and surrounding components. Support the engine temporarily with a hoist or jack before securing the mounts. Step 2. Securing the engine. Bolt the engine to the engine mounts, ensuring even tightening. Use a torque wrench to tighten mount bolts to manufacturer specifications. If using aftermarket or performance mounts, ensure they provide proper vibration damping. Step 3. Connecting the drivetrain. If installing a manual transmission, ensure proper engagement of the clutch and flywheel. For automatic transmissions, align and secure the torque converter to the flex plate. Connect the drive shaft or chain for motorcycles to ensure power transfer. 3. Connecting essential systems. Once the engine is securely mounted, all supporting systems must be connected and tested. Fuel system. Attach fuel lines securely to the fuel pump, injectors, or carburetor. Check for fuel pressure and leaks before startup. Cooling system. Install the radiator, coolant hoses, and thermostat. Fill with coolant and check for leaks. Electrical system. Connect the battery, ignition coil, and spark plugs. Attach the engine control unit, ECU and sensors, oxygen, map MAF, crankshaft position, etc. Check for proper grounding to avoid electrical malfunctions. Exhaust system. Install the exhaust manifold, catalytic converter, and muffler. Ensure proper sealing to prevent exhaust leaks. Lubrication system. Fill with engine oil, ensuring the correct viscosity. Prime the oil pump to prevent dry starts. 4. First start and testing. After the installation, testing ensures that the engine operates correctly. Step 1. Initial start. Crank the engine without fuel to build oil pressure. Start the engine and let it idle while monitoring for leaks or unusual noises. Step 2. Performance check. Observe RPM, stability, and check for Monitor temperature and oil pressure using gauges or diagnostic tools. Inspect for fluid leaks in fuel, oil, and coolant systems. Step 3. Rotor load. Test. For vehicles, conduct a test drive to assess acceleration, shifting, and stability. For industrial machines, test the engine under load to confirm reliability. 5 common challenges and solutions. Issue 1. Engine misalignment. Problem: vibrations, excessive wear, or drivetrain failure. Solution: use proper alignment tools and torque mounts evenly. Issue 2. Electrical failures. Problem: engine fails to start or ECU errors. Solution: double-check all wiring connections and ensure proper grounding. Issue 3. Fuel delivery problems. Problem: engine stalls or won't start. Solution: test fuel pressure and inspect fuel lines for clogs or leaks. Issue 4. Overheating. Problem: engine temperature rises rapidly. Solution: ensure proper coolant levels and air pockets are bled from the cooling system. 6. Special cases in engine installation. Performance engine installation requires reinforced mounts to handle increased power. May need an upgraded cooling system for heat management. ECU tuning is often necessary to optimize fuel-air ratios. Engine swaps different engine from stock. Custom mounts may be needed for fitment. Wiring harness modification is required to integrate sensors and the ECU. Transmission adapters may be necessary for compatibility. Motorcycle engine installation. Chain alignment is crucial for power transfer. Air cooling versus liquid cooling affects radiator placement. Weight balance must be checked for handling stability. Conclusion: engine installation is a meticulous process that requires careful preparation, precision in mounting, and thorough testing, whether it's a stock replacement, performance upgrade, or engine swap. Attention to detail ensures smooth operation and longevity. Advanced Engine Installation Guide. Installing an engine, whether in a car, motorcycle, truck, or industrial machinery, requires precision, mechanical knowledge, and attention to detail. This guide delves deeper into specialized aspects such as performance engine installs, engine swaps, electrical integration, and post-installation tuning. 1. Engine mounting and alignment. Proper mounting and alignment are crucial for engine balance, vibration reduction, and drivetrain efficiency. Types of engine mounts. Rubber mounts. Common in stock vehicles, absorb vibrations well. Hydraulic mounts. Found in luxury and modern vehicles for smoothness. Solid mounts. Used in race cars but transfer more vibration. Polyurethane mounts, a middle ground between rubber and solid mounts, used in performance applications. Alignment considerations. Engine angle and tilt. Ensures the drive shaft and transmission are correctly aligned. Centering the crankshaft reduces drivetrain stress. Clearance checks. Make sure the engine doesn't interfere with other components. Firewall, suspension, radiator. Tools required. Engine hoist crane. Precision measuring tools. Dial indicators. Laser alignment tools. Torque wrench. Common mistakes. Over-tightening mounts, leading to excessive vibration. Misalignment, causing premature wear on belts, pulleys, and drivetrain components. 2. Drivetrain integration. After mounting, the engine must properly connect to the transmission, drive shaft, and axles. Manual versus automatic transmission connection. Manual. Align clutch, pressure plate, and flywheel correctly. Automatic. Ensure torque converter is properly seated on the flex plate before bolting it to the engine. Drive shaft and axle considerations. Ensure drive shaft angles match manufacturer specs to prevent vibrations. CV joints and U-joints should be properly lubricated and aligned. On motorcycles, chain alignment must be checked for even wear. Common issues and fixes. Engine running but car won't move. Check if the torque converter or clutch is properly engaged. Drive shaft vibration at high speed. Recheck drive shaft angles and balance. 3. Electrical and ECU integration. Wiring and sensor connections. Reconnect all engine sensors, oxygen sensor, crankshaft position sensor, knock sensor, etc. Rewire the ignition system, coil packs, spark plugs, distributor for older engines. Battery grounding is crucial. Bad grounds cause electrical failures. ECU reprogramming and tuning. If installing a different engine swap, the ECU may need remapping or a standalone system. Performance builds often require air-fuel ratio AFR adjustments using ECU tuning software. For modern engines, OBD2 scanning tools help diagnose sensor issues. Common ECU problems. Check engine light after install. Double-check sensor wiring. Engine cranks but doesn't start. Possible immobilizer or key programming issue. For cooling system setup, a properly functioning cooling system prevents overheating and ensures optimal performance. Installation steps. Mount the radiator securely. Check for clearance with engine pulleys. Connect coolant hoses without kinks or leaks. Install thermostat to regulate engine temperature. Bleed air from the system after filling with coolant. Air pockets can cause overheating. Cooling system mistakes and fixes. Engine overheating after install. Likely due to air pockets. Rebleed the system. Coolant leaks. Check hose clamps and water pump seals. 5. Fuel system integration. Fuel delivery must be set up correctly to avoid engine starvation or flooding. Fuel system considerations. Fuel injectors versus carburetors. Modern engines use electronic fuel injection (FE), while older engines use carburetors. Fuel pump capacity. High-performance engines need high-flow fuel pumps. Fuel pressure regulation. Use a fuel pressure gauge to verify proper PSI. Fuel system issues and fixes. Engine won't start. Check fuel pressure at the rail. Running too rich or lean. Adjust the ECU or air-fuel mixture. 6. First startup and testing. Pre-start checklist. Double-check all bolts and fasteners. Ensure proper fluid levels, oil, coolant, transmission fluid. Prime the fuel system by cycling the ignition a few times. Rotate the crankshaft manually to check for resistance. Startup procedure. Crank without fuel. Builds oil pressure before first ignition. Start and idle. Check for leaks, misfires, or unusual noises. Monitor engine parameters using an OBD2 scanner or diagnostic tool. Initial test drive for vehicles. Keep RPMs low during the break-in period. Monitor engine temperature and oil pressure. Listen for clunks, vibrations, or misfires. Performance and tuning after installation. Fine-tuning the engine. Adjust timing and ignition maps for maximum efficiency. Use a dyno or road tuning to optimize power and fuel economy. Monitor AFR air-fuel ratio, using a wideband O2 sensor. Break-in period for new or rebuilt engines. Keep revs under 4,000 RPM for the first 500 to 1,000 miles. Change engine oil after 500 miles to remove break-in debris. 8. Special cases. Engine swaps and high-performance builds. Engine swaps replacing a different engine model. Custom engine mounts and transmission adapters may be needed. The wiring harness and ECU may require custom reprogramming. Clearance issues may require modifying the chassis or high-performance engine installs. Consider reinforced mounts for added torque. Upgrade the fuel injectors and pump for higher horsepower engines. Install an oil cooler for better heat management. 9. Troubleshooting common issues. Issue possible cause fix. Engine won't start, no spark, no fuel, or immobilizer. Issue check ignition, fuel pressure, and ECU. Vibrations at idle. Misaligned engine mounts. Realign and torque mounts properly. Transmission won't shift. Clutch or torque converter misaligned. Inspect clutch engagement or fluid levels. Overheating air pockets and coolant. Bleed cooling system properly. Check engine light sensor wiring issue. Scan ECU codes with OBD2 tool. Mastering engine installation, advanced techniques and considerations. Engine installation is a complex process that involves mechanical, electrical, and performance-related aspects. Whether you're installing a brand new engine, swapping in a high-performance powertrain, or rebuilding an existing one, mastering the process requires attention to detail. This guide will explore advanced installation techniques, troubleshooting complex issues, performance tuning, and specialty installations like hybrid electric powertrains. 1. Engine mounting, precision and reinforcement. Advanced engine mounting techniques. While standard mounts suffice for daily driving, performance and high-torque engines require additional reinforcement. Key considerations for secure mounting. Solid versus semi-solid mounts. High-performance builds may use aluminum or urethane mounts instead of rubber. Custom mount fabrication and engine swaps. Custom brackets or reinforced cross members may be needed. Load distribution and chassis stress. Reinforce the subframe to handle additional torque. Drivetrain alignment. Adjust the pinion angle for rear-wheel drive vehicles to reduce stress on the drive shaft. Potential problems and solutions. Excessive engine vibration. Consider softer polyurethane mounts or additional vibration dampening. Cracking or bending of mounting points. Reinforce with steel plates or weld-in braces. 2. Electrical system and ECU integration. Modern engines rely heavily on electronic control units, ECUs sensors, and fuel injection systems. Proper installation ensures full functionality and prevents electrical issues. Advanced ECU integration. Stock ECU reprogramming. When installing a performance camshaft or turbo, an ECU remap is often required. Standalone ECS for custom swaps or racing applications. Systems like Hailtech, AEM, or Motec provide full tuning control. CAN bus compatibility. Many newer engines rely on digital communication networks, so the new ECU must be compatible with the vehicle's systems. Wiring harness modifications. Sensor relocation. Custom mounts may require rerouting the crankshaft or oxygen sensors. Wire length adjustments. Use proper shielding and heat-resistant sheathing for reliability. Fuse and relay adjustments. Upgraded engines may need higher amperage fuses and relays to support fuel pumps or ignition systems. Common electrical issues and fixes. Starter clicks but engine doesn't crank. Check grounding and battery voltage. Engine starts but runs poorly. Scan for ECU error codes using an OBD2 reader. Dashboard warning lights, ABS, traction control, etc. Confirm that combust signals are properly connected. 3. Advanced cooling system techniques. Performance engines and high-power builds require enhanced cooling to prevent overheating and engine knock. Cooling upgrades and best practices. Aluminum radiators provide better heat dissipation than stock copper, brass units. High-flow water pumps ensure faster circulation of coolant to prevent hot spots. Oil coolers, essential for turbocharged engines or track cars. Dual electric fans improve airflow, especially in high-horsepower builds. Thermal wraps and heat shields reduce heat transfer from exhaust components to surrounding systems. Troubleshooting cooling issues. Engine overheats at idle. Check if cooling fans activate properly. Coolant leaking from the engine. Possible head gasket failure or water pump seal leak. Air pockets causing inconsistent temperature. Use a vacuum coolant filler to remove trapped air. 4. Fuel system upgrades and tuning. Fuel delivery must match the engine's horsepower and torque output. Improper fuel pressure or flow can cause lean conditions, knocking, and engine failure. High-performance fuel system considerations. Fuel pump upgrades. Turbo and supercharged engines require higher pressure and flow rates. Fuel injector sizing. Use this formula to calculate the required injector size. Injector size cc per minute equals horsepower times BSFC times 10.5 number of cylinders. Injector size cc per minute equals number of cylinders, horsepower times BSFC, 10.5. BSFC equals brake-specific fuel consumption. Usually 0.54 NA engines and 0.6 to 0.7 for forced induction. Fuel pressure regulators, essential for fine-tuning fuel delivery. Ethanol E85 compatibility. If using E85, ensure the fuel lines, injectors, and pump are ethanol safe. Troubleshooting fuel system issues. Engine misfires under load. Check fuel pressure and injector flow. Runs rich or lean. Use a wideband O2 sensor to monitor air-fuel ratios. Fuel pump winds excessively. Possible clogged fuel filter or pump overheating. 5. Turbo and supercharger installation considerations. For high-performance builds, forced induction provides significant power gains, but requires careful tuning. Installation checklist for boosted engines. Proper turbo sizing matching the right turbo to the engine prevents lag or excessive back pressure. Intercooler installation reduces intake temperatures to prevent detonation. Blow-off valve or wastegate setup. Prevents overboosting and engine damage. Boost controller and tuning. Electronic boost controllers allow precise adjustment of pressure. Common boosted engine issues. Turbo lag. Consider a smaller turbo or ball bearing design. Boost spikes. Ensure wastegate is properly set. Detonation under boost. Adjust ignition timing and run a richer fuel mixture. 6. Hybrid and electric engine installations. With the rise of EV conversions, more enthusiasts are swapping gasoline engines for electric motors. EV conversion considerations. Motor selection. Choose between AC or DC motors depending on power needs. Battery placement and cooling. Ensure proper weight distribution and thermal management. Regenerative braking system. Many EV controllers support regen braking for efficiency. Common EV swap issues. Insufficient battery range. Upgrade battery pack capacity. Excessive weight balance issues. Distribute batteries evenly across the chassis. Motor overheating. Consider liquid cooling instead of air cooling. 7. Final testing and break-in procedures. Final pre-flight checklist before driving. Retorque all critical bolts. Engine mounts, transmission, drive shaft. Confirm all fluid levels. Engine oil, coolant, transmission fluid, brake fluid. Scan the ECU for error codes before startup. Verify fuel pressure and ignition timing set-in. Engine break-in process for new rebuilt engines. First, 500 miles. Keep RPMs below 4,000 and avoid heavy acceleration. First oil change. Replace oil and filter after initial break-in to remove metal shavings. Gradual load testing. Slowly introduce higher RPMs in load conditions. Common break-in issues. Excessive oil consumption. Piston rings may not be sealing properly. Consider a harder break-in. Low compression. Possible valve seating issue. Perform a leak down test. Conclusion. Engine installation is an art that blends mechanical precision, electrical integration, and performance tuning. Whether installing a stock replacement, high-performance racing engine, or an EV powertrain, careful plan. Mastering the art of engine installation. Comprehensive guide to performance and reliability. When it comes to engine installation, the process goes far beyond just securing a motor into place. Successful engine installation requires a deep understanding of engine mechanics, electrical integration, safety standards, and fine-tuning for performance. Here's an extended guide on advanced considerations for installation, covering performance enhancements, custom modifications, and post-installation troubleshooting. 1. Performance upgrades during installation. High-performance components, enhancing power and reliability. When installing an engine, it's the perfect opportunity to incorporate performance components that maximize power, efficiency, and longevity. This includes enhancing engine internals and auxiliary components, performance internal engine components, forged pistons and rods. Forged pistons and rods are stronger and can handle higher horsepower and torque, reducing the risk of failure under pressure. They are ideal for turbocharged, supercharged, or higher revving engines. Upgraded camshaft and timing components. The camshaft controls the timing of the engine's intake and exhaust valves. Upgrading to a performance camshaft can increase airflow and overall engine efficiency. Ensure proper timing and clearances to prevent interference between the piston and valves. High-flow cylinder heads. Performance cylinder heads can greatly improve airflow, leading to more power. Consider larger valves, polished ports, and more aggressive camshaft profiles. Cylinder head installation requires precision, as even slight warping or improper sealing can lead to air leaks or coolant loss. Upgraded crankshaft and bearings. A performance crankshaft can withstand higher engine speeds RPM and increased load. It's often used in racing and motorsport applications. Turbocharging and supercharging. Turbochargers and superchargers force more air into the engine, significantly increasing power output. However, they require upgraded components such as stronger rods, pistons, and better cooling systems. Pay close attention to the boost levels, and ensure the engine is designed to handle the extra power. 2. Custom engine swaps. Adapting to new powertrains. Custom engine swaps can involve serious modifications, but with the right tools and preparation, they can result in a completely new driving experience. Here are some advanced techniques for a seamless engine swap. Adapting the engine bay for a new engine. Clearance modifications, custom mounts, and possibly even cutting or reshaping parts of the engine bay may be necessary for a new engine. Cooling system modifications. When swapping in a larger or more powerful engine, your current cooling system may not be up to the task. Upgrading to a larger radiator, additional fans, or a more powerful water pump is essential to handle the increased heat. Transmission and drivetrain adjustments. For engine swaps, especially those involving a change in engine type, for example, from an inline to a V configuration, the transmission often requires adjustments. You may need adapter plates to connect the new engine to your existing transmission, or an entirely new transmission if the bolt patterns do not match. Driveline length and angle adjustments are sometimes necessary, particularly when swapping from a front engine to a rear engine configuration, or vice versa. 3. Advanced fueling system modifications. Fuel delivery systems must be carefully tailored to match the engine's needs, especially if you're working with high-performance or boosted setups. Upgraded fuel injection systems. Injector sizing. For high-output engines, fuel injectors must be chosen based on the desired power output. A larger injector ensures enough fuel is delivered to match increased airflow. Direct injection systems. Modern engines often utilize direct injection for increased power and efficiency. When doing an engine swap or performance build, you may need to integrate direct injectors and a compatible ECU to manage them. Fuel pressure regulators and adjustable systems. An adjustable fuel pressure regulator (FPR) allows for finer tuning of fuel delivery, which is particularly helpful in custom builds where performance demands fluctuate. Ensure that fuel lines are reinforced and resistant to high pressure, as higher performance systems often run at elevated pressures. Upgraded fuel pumps. A high-flow fuel pump is necessary for engines making substantial power, particularly for forced induction applications. Ensure the pump is rated for the required flow and pressure. For exhaust system design for maximum flow. An efficient exhaust system helps release the combustion gases quickly, reducing back pressure and improving engine efficiency. Header and exhaust manifold upgrades. Performance headers are often used to increase the exhaust flow, especially in modified engines. They are typically made of stainless steel or ceramic-coated materials for better heat resistance and durability. The primary goal is to reduce back pressure and allow exhaust gases to exit as freely as possible, which improves engine performance. Downpipes and catalytic converters. For turbocharged engines, a high-flow downpipe is essential for maximizing power and turbo spool time. If you're upgrading to a performance exhaust system, make sure you select a high-flow catalytic converter that reduces restrictions, while still complying with emissions standards if applicable. 5. Advanced tuning, maximizing engine output. Once the engine is installed, the next crucial step is tuning it to maximize performance, reliability, and fuel efficiency. ECU tuning and remap. Performance tuning is an essential step after installing a high-performance or swapped engine. A professional tuner can adjust the engine's air-fuel ratio (AFR), ignition timing, and other parameters for maximum performance. Many tuners use wideband O2 sensors and dyno testing to ensure proper fuel mixture and ignition timing. If installing a forced induction system, turbo or supercharger, boost control mapping must be fine-tuned to prevent knocking and overboost conditions. Standalone engine management systems. Standalone ECUs, such as Hailtech AEM or Motec, provide more flexibility than factory ECUs, and allow for detailed tuning of all aspects of the engine, from fuel delivery to timing. Ensure proper wiring of the standalone system and integration with sensors, boost control, and data logging systems. 6. Post-installation testing and tuning. Engine breaking in. After the engine is installed and before heavy driving or racing, it's essential to break in the engine to ensure the longevity of components like pistons, rings, and bearings. For the first 500 to 1,000 miles, keep the engine revs below 4,000 RPM and avoid sustained high loads. Perform an oil change after the first 500 miles to remove any debris or fine metal particles created during the break-in process. Engine compression testing. After initial startup and during the tuning phase, it's important to perform a compression test to ensure that the engine is building proper compression and that there are no issues with cylinder sealing. Coolant and oil temp monitoring. During test drives or dyno sessions, monitor the coolant and oil temperatures to ensure that the cooling system is handling the engine's heat output. 7. Troubleshooting common post-installation issues. Even after all the careful planning and work, issues can arise. Below are some of the most common problems and their solutions. Engine overheating. Check for coolant leaks, failed thermostat, or a clogged radiator. Upgrading to an aluminum radiator and electric fans often resolves cooling issues in high-performance builds. Engine misfire or rough idle. A misfire can be caused by several factors, including faulty spark plugs, bad fuel injectors, or incorrect timing. Check spark plug condition. Ensure that fuel injectors are functioning properly, and confirm that the timing is set accurately. Excessive oil consumption. This could indicate worn piston rings, improper break-in, or an issue with the PCV system. Perform a leak down test to check for internal engine leaks. 8. Long-term maintenance and upkeep. After your engine installation is complete, maintaining it is crucial to ensure longevity and prevent premature failure. Regular oil changes. Change the oil every 3,000 to 5,000 miles or as recommended by the manufacturer. Use high-quality synthetic oils for performance engines. Timing belt, chain maintenance. If the engine uses a timing belt, it must be replaced every 60,000 to 100,000 miles to avoid catastrophic engine damage. Fluid checks and top-ups. Regularly check and top off the coolant, brake fluid, and transmission fluid to ensure that all systems operate optimally.